lecture. All right, well, happy Monday. It is week 2, and we'll get started here. I have posted homework, so I'm hoping you guys have started, or at least taken a look at it, at least downloaded the file and looked at it, and then you'll have to work on it this week. Okay, let's go ahead and get into today's topic, which is cross-validation. Okay, so in Friday's lecture, we ended the lecture just kind of, we said, you know what, we can try out these, get a nonlinear response. We can fit a few different models, and so we fit several polynomial models to the Olympic data. Okay, and so again, the Olympic data is, we're looking at the winning race time for the 100-meter foot race, and this is what we have. And we left off on Friday. We just said, let's fit a linear model, a quadratic, cubic, polynomial model of degree 4, 5, and 6, just to kind of see how these things fit. And so this is where we left off, and we said, which model is the best model? Which is the model that we should have used here? And so, in kind of your classical approach for this is that you'd have to kind of think about the variables, think about what these relationships mean, and does it make sense? Does it make sense for the race times to have kind of a quadratic or cubic relationship over time in terms of like the years that have passed? Does it make sense to have a 6th order relationship? And these things are hard to answer and hard to, reason about or think about. In some cases, it makes sense, right? Like if you're throwing a ball in the sky, it says, oh yeah, we know the effect of gravity over time, and you're going to have this kind of this quadratic relationship and things like that. But other things like, people seem to be getting faster over time as far as winning race times go. And what's the exact relationship there? Okay. And so, you have tools like AIC and BIC and things like that to help in the model selection procedure. But what we're going to take a look at today is cross-validation. And what it does is it removes a lot of the kind of the skill that comes in this decision-making process. But, I guess the flip side is that it removes, sometimes these decisions are a little bit arbitrary that we make. We just say like, yeah, you know what, this feels good, this doesn't feel good. And so it is a little bit arbitrary, and what we use is a validation strategy. And this is often kind of the tool of choice as far as a lot of machine learning models go, is that sometimes the models get so complicated that it's difficult to really reason and say, you know what, this model objectively makes more sense than this other model. Okay, I mean, sometimes we're in a situation where you can do that. A lot of times you're not. And so rather than just saying, well, I like this one more and having an arbitrary thing, we use this cross-validation approach. And so kind of from a high-level perspective, what cross-validation does is it takes the observed data that you have, and it's going to split it into 2 parts. It splits it into a training set and a validation set, okay? And we use the training set to fit the model, right? And so, as far as linear regression goes, fitting the model just means finding the parameters, like your intercept and your slope or whatever other coefficients you have, finding the coefficients in your vector W hat. That's the fitting the model. In other cases, maybe there's more terms that you have to estimate when it comes to fitting the model, but that's what you use the training set for. And then once you're finished fitting the model with the training set, what you're going to do is you're going to take that fitted model and you're going to make a prediction for the validation set. Okay, you're going to say, what does this line predict for this point in the validation data? Okay, and we're going to use some kind of metric, okay, some kind of value that measures how well our model performed at making a prediction. Okay, so a common choice is just the mean squared error. We're going to take that and we're going to say, all right, this is how we're going to measure whether our model did a good job or bad job of predicting. Other choices exist as well. And we're going to do this for every kind of model that you want to test. All right, and then you compare the metrics at the end of the day, and you can kind of choose the best performing model from there. So, so kind of one of the simplest ideas is LeaveOneOut Crossvalidation. Okay, and so as far as cross-validation goes, one method is called LeaveOneOut, and basically what this does is it takes your observed data and it leaves one observation out. Okay, so it removes one observation. The rest of it serves as your training data. Okay, the training data is going to be all of the data that's available minus one observation. The one that you leave out is going to serve as your validation point later on. Okay, and you're going to every data point in your data set will have a turn at being the validation point, okay, or the validation set. And so you're going to have to fit a total of n different training / validation sets. So if you have a very, very large data set, LeaveOneOut cross-validation is a bit undesirable just because you're going to have to fit the model so many times, right? So if you got like 100,000 or 1,000,000 observations, LeaveOneOut probably not the best. But just for an example, I'm going to do a toy example with 4 data points. And so we're going to just put one observation at a time as the validation set, and I'm going to just try to illustrate how the LeaveOneOut cross-validation goes. Okay, so my data points are 1, 2, 3, 4 for X, and the predicted or the actual values are 1, 3, 2, 4. Okay, and what we're going to do is we're first going to use number 4 as our validation point. Okay, and we're going to train on 1, 2, 3, and we're going to leave out number 4. All right, and so to kind of illustrate how this is going to go, as far as the X points go, my training X is going to be everything but index number 4. Okay, and then the validation set is going to be everything, will be just index number 4. Okay, and then the training data T will be everything but index number 4, and the validation T will be index number 4. Okay, so I'm going to take the training data, I'm going to take the training X, which is going to be 1, 2, 3, and the training T, which is going to be 1, 3, 2. I'm going to put those two together into a data frame, and we're going to call that training data. Right, and now I fit a model based only on the training data. So we're not taking the full data set. We're only taking these 3, 1, 2, 3, and 1, 3, 2 to fit my model. Right. So if I were to fit all 4 data points, 1, 2, 3, and 4, this would be the line of fit. Okay, this red line would be the line of fit. But I'm not using all 4 data points. I'm using only these 3 data points. Okay, I'm using only data points 1, 2, and 3. And if you fit a line for 1, 2, 3, this is going to be the line of best fit. Right, so this is it for all 4 data points. But when you only have 3, this is the line that's going to get fit. Okay, so the line that gets fit is y equal to 1 plus 0.5x. And then what we do is we take the validation point. All right, our validation point is the point 4, 4, and we plug that in and we say, okay, well, what did you predict? Okay, this blue line, right, is the line that gets fit just to these 3 points. Right, so if you use that and you have 1 plus 0.5 times 4, right, so this fitted line is 1 plus 0.5x. Okay, when you plug in number 4 there, you're going to predict the value 3. Okay, and then the actual value at data point 4 is 4. And so the error here is going to be 1, and you square that, your squared error is 1. Right? Does that make sense? What's going on here as far as where this blue line came from? Okay, the blue line came from fitting a linear model just to these 3 data points. Okay, and then we calculate the squared error, and so we do, so we get a squared error of 1 here. And And so just to kind of store this in code, this is how it works, right? So the LeaveOneOut model LLO is going to be, we're fitting a linear model where we're using the training data to predict it, to create the model. And then once you have that, I'm using the predict function. And we're going to say, all right, I want to make a prediction using this model, using the LeaveOneOut model. And I want to predict it for this new data point. Okay. And the data point is going to be for X equal to, you know, our validation X, which is just the point number 4. Okay. And that's going to create our prediction. Okay. Prediction is T hat. And then the squared error, that is this, the squared error is going to be the difference between the actual validation point, in our case is 4, minus the predicted value T hat. We're going to square that difference and store that in squared error. Okay. And I initialized way back here, I initialized my total squared error to be 0. All right. And so I'm going to just kind of take the total squared error, which is currently 0, and add on, this is going to take on the value. This is going to be 1. And so far my total squared error is 1. All right. Why don't I go ahead and give you your first quiz answer for today. First quiz answer today is the letter E. E as in elephant. E as in elephant is your first view quiz answer for today. E as in elephant. All right. And so I repeat this process, okay, for each of the data points. So again, here is the line fit to all 4. But what we're going to do is we're going to remove, this time I'm going to remove the third data set, right? I'm going to remove this one. And so now we're only going to have points 1, 2, and 4. And so if I do that, the best fitting line for points 1, 2, and 4 looks like this, okay? It's y equals 0.5 plus 0.92857. So I'm just fitting a line to just these 3 data points, 1, 2, and 4. And this is what we have. Okay? And so if I have that, then we're going to say, okay, what is the predicted value for point number 3? Okay, so if you put in point number 3, it says, you know what, we would have predicted 3.28571. Okay, that would be the value you predict for point number 3, right? And the actual value, though, in our data set is the value 2. Okay, so you have a difference of negative 1.28571, right? So the actual value minus the predicted value is negative 1.28571. And if you square that, you're going to get a squared error of around 1.65. Okay, and again, this is from just, we're fitting a line to these 3 data points, and we're plugging in back the original data point, and we're taking that difference and we're squaring it. Okay, we do it for each data point gets a term being left out. So this time we're going to leave out this data point. We're going to leave out point number 2. Okay, so I'm going to cover this up. Okay, and so if I remove that and I say, all right, fit a line to the remaining 3 points, this is the line that best fits the remaining 3 points. Okay, the line that fits the remaining 3 points best looks like this, and we get this. This is the intercept, and this is the slope. And if you plug in the number 2, okay, then you get yeah. So you get we're predicting 1.71. The actual value is 3. Okay, so we have a difference of 1.29, or 1.28571. That's the difference there. If you square that, you get a difference of 1.6531, and we're going to tack that on. Okay, so we're going to do that. And then lastly, if we remove this data point, okay, we remove point observation number 1, we fit it linear fit on just points number 2, 3, and 4. This is the line of best fit. Okay, here y is 1.5 plus 0.5x. Okay, and we're going to say, all right, what value would you have predicted for point number 1? If you plug in x equals 1 here, we would have predicted a value of 2. Okay, and the actual value in this case is the value 1. Okay, and so we do that. And so if you add up all of these total squared errors, so we have 1 plus 1.6531 plus 1.6531 plus 1 adds up to 5.306. And if you divide that by 4, because we have a total of 4 data points, our mean squared error for our cross-validation mean squared error is 1.326. 1.326, yeah. Okay, or 1.3265, I should say. All right, we feel okay about all of this? Okay, and so there, you don't have to actually do this manually like this. All right, I drew all of those slides, which was a fair amount of work, just for kind of illustrative purposes. But R has some built-in functions here. Okay, and so you could load up library boot. Okay, inside library boot, there's a cross-validation function, and first you fit a GLM, generalized linear model, to your full data set. Okay, so here I'm going to fit it to all 4 data points. Okay, so this is my all data. I fit a GLM. This is my linear model. And I'm going to run crossvalidation.glm using the data frame all data and the linear model. Okay, and the results for the mean squared error and cross-validation is stored in this in the result delta 1. Okay, delta 1. And so if you do that, you get LeaveOneOut cross-validation. The LeaveOneOut cross-validation score is 1.3265. Okay, and so that aligns exactly with what we got if we did it manually. Right, so if we did it manually, we got 1.3265, and if we just ask R to do it using their Bootstrap library, we get the same value here. Okay, which is great. Okay, because this is probably what you would use in just general production, whereas, just for illustration and understanding where these numbers come from, it's nice to be able to kind of recover the same values yourself. Okay, and so, just to be clear, you wouldn't use cross-validation if you only have one model. Okay, if you have only one model and you're going to say, this is the model I'm fitting, it doesn't really make sense to use cross-validation in that context. Cross-validation is really a tool that we use to compare one model to another. Okay, so basically what you would want to do is you say, okay, well, here's one model. This is the linear model. And what's my cross-validation score for this linear model? Okay, here's an alternative model, right? Maybe we want to try quadratic model, or maybe some kind of log fit. Okay, and if we do that, we would run cross-validation on the alternative model, and you would get another value, right? You would get some kind of score, cross-validation score, and you'd compare the cross-validation score of this model versus the cross-validation score of this model. Okay, in much the same way that you might use something like AIC to compare one model score to another model score, you use cross-validation in a similar sense. Okay, the cross-validation applied to just one model by itself is not very useful. Okay, it's only useful in the context of comparing one to another. Okay, and so this is just kind of a summary diagram of kind of all of the linear model fit 4 times, where each data point got to serve as the test point or the validation point. Okay, so if you train it on these points, and the validation point is observation 1, observation 2, observation 3, observation 4. These are your squared errors, and if you add these values up, 1, 1.6531, and so on and so forth, you're going to get this as your total squared error. And then when you take the average, you're going to get this as your mean squared error. Okay, and so it's always, we're fitting it to everything that was after you removed that one point, and then you go back and you try to calculate the error for the one you left out. That's what LeaveOneOut cross-validation does. Okay. Again, the problem is that if you, okay, so yeah, this is all to say, you'd fit it to other models, you calculate your cross-validation score, and you'd compare models in that way. Okay. Again, the issue with LeaveOneOut cross-validation is that if you have a very large data set, you're going to have to fit the model n times, which can be computationally very expensive. You also kind of run into, you can run into some problems with just having almost all of your, the data sets, the training data almost always looks like every other training set, because there's only going to just basically be one observation that's different, or two observations that are different from one training set to another. And so if, you know, kind of variable collinearity and stuff like that is an issue, the cross-validation values can exhibit some instability. But so, you know, a popular alternative to LeaveOneOut cross-validation is Kfold cross-validation. Okay, and so Kfold cross-validation says, you know what, let's take our data set, okay, and split it into k, you know, approximately equal-sized blocks. All right, and then each block will get to serve as the validation set. Okay, so maybe you'll take, if you have a large data set, you might split it into 10 blocks, and these would be kind of randomly selected, and you would use each block as, or each fold as a validation set. Okay, so just to kind of illustrate, we're going to do maybe 4-fold cross-validation for the Olympic data, and I'll illustrate how cross-validation works for our Kfold cross-validation works here. All right, and so just kind of our diagram here is you take your data and you split it into four sets here, approximately equal. And during your first iteration, maybe you'll set this one to be your validation set, and you're going to train on the remaining 3 blocks. Okay. During the second iteration, you use the second set as your validation set, and then you got you train on the other ones, and so on and so forth. Okay. Now, with Kfold cross-validation, the results are going to be subject to which data points end up in the validation set. Whereas LeaveOneOut cross-validation, if 2 people ran LeaveOneOut cross-validation, they're going to get the exact same results, okay? Because person number 1, each data point served as a validation set, or validation point exactly 1 time. And for person number 2, each validation point, or each point in the data set served as a validation point exactly 1 time. Okay. Whereas with Kfold cross-validation, if this person had a different starting random seed than this person, then you know, every point serves as as part of the validation set, but validation set 1 for this person is going to be different from validation set 1 for this person, just because of the random assignment there. And so you're going to get slightly different answers. They're going to be comparable, but they're going to be slightly different. It's going to be subject to the randomness of which data points end up in each validation set. Okay. So anyway, we'll take a look at the Olympic data. All right. And so in the Olympic data, we have 28 rows and 2 columns. And you know, our first is 1896, and I think it goes up to 2008 or something in the Olympic data. And so we'll take a look at the fits here, or maybe 2012. Okay. All right. So here is here's what we do, and so just to kind of illustrate this, we're going to divide the data into 4 random blocks. So here I'm performing Kfold cross-validation manually, and again, kind of in a production setting, you would probably use the library boot, and you'd use the cv.glm. You have the option to specify Kfolds and things like that. Okay, and so we're going to split the 28 data points into 4 different random blocks. And each of those blocks will have a turn as serving at the validation set, right? So each block will have 7 points, 7 randomly selected points. And we're going to just for illustration, I'm going to fit a linear model, quadratic, cubic, 4th order, 5th order, 8th order, and just for fun, we'll fit a 17th order polynomial, okay? Just so you can kind of see that like fitting higher degree polynomials is not always gonna result in better outcomes here, okay? And what we're gonna do is we're gonna calculate the total squared error for each model, for each validation set, and we're gonna calculate the cross-validation score by kind of averaging the total squared error for each model, okay? And we're gonna compare those cross-validation scores from each of the different models. Okay, all right, so before I get into the next part, let me go ahead and give you your next quiz answer. Next quiz answer is the letter D, D as in dog. D as in dog is your second quiz answer for today. Second quiz answer. Okay, so here I just did a set seed 5, and then I shuffle the indexes 1 through 28. Okay, so that's going to sort them 1 through 20, or shuffle them up. Okay, and then we're going to take the first 7 and put them into set A, the next 7 into B, the next 7 into C, and the next 7 into D. Okay, and I'm going to combine them all into a list. And we've got a list of sets: set A, set B, set C, and set D. And so this will have all 28 rows, but just kind of all shuffled up. You got 7 random in set A, 7 random in set B, 7 random in set C, and 7 random in set D. Okay. Next slide is a bunch of, not this one. Next slide is a bunch of code. All right. And so here, this is where we're going to store the results for the cross-validation scores. Okay. And so because I have 4 sets, I'm going to fit each of these models 4 times, and I'm going to store kind of your squared errors values into each of these things. So we got linear, quadratic, order 3, 4, 5, 8, and 17 as a kind of placeholders to store all of the different models here. Okay. All right, and so this is basically the code, and I kind of just want to run through it to show you how cross-validation is going to work here. You're going to do something similar in your homework. Okay, so first we're going to just take one of the sets. Okay, so I'm going to run this 4 times, and so during the first iteration, we're going to take the first set. In this case, it'll be set A, and then in the next iteration, when we run the for loop again, we're going to take set 2, and so on and so forth. And we're going to set that to be our validation index. Okay, we're going to have the validation index. And so the training data is going to be everything in our X variable, Olympic $year, where we remove the validation index. So we're going to do minus validation index for the training X and training T. And then, and the validation set is going to be, basically the X variable just of those validation index, and the time variable just for the validation index here for our validation T. Okay. I create a training set and validation set for our data frames. My data frame will be X is the training X and T is the training T. And for my validation set, we're going to use those in the validation X and the validation T, right? So this is going to serve as my training and validation data. And N here is 7 in each of these cases, but just in case you have something slightly variable, I just have, we're going to take the length of the validation index here, right? And then I'm going to fit different models using the training set, right? So I'm going to, the first model I fit is a linear model. I'm going to say use LM, and we're going to fit predict T based on X using the training data, right? And that's going to be my linear model. And then once I have this model, I'm going to use that model to make a prediction, okay? And I'm using, I'm going to predict for the data in my validation set, okay? And so, it's important when you do cross-validation that when you make predictions, you're predicting for values that were not used as part of the training data, right? So, if you're only using predictions on your training data, you can end up overfitting your training data. So here we're making predictions based on the validation data, which was not used in the training process, and we use the predict function. So I guess part of this, I went over this quickly. I'm assuming you guys are comfortable with kind of the concepts in 101A. I didn't cover like exactly how LM and predict work, but I'm assuming you guys have seen these functions before, and you're comfortable with, you know, using predict, plugging in some model that you trained earlier, and then providing it a data frame of new values. Right? Okay, so anyway, when you use the predict function, you're going to get a vector of predicted values. And so this is going to be my vector t hat. Okay, and then to kind of get my sum of squared errors, I'm going to take my actual data points, which is in my validation set. Okay, validation set $t. Okay, that's in the data frame. And we're going to subtract off the predictions, and we're going to square that up, and we're going to sum all of those and divide by n. In our case, divide by 7. So we're going to get, so actually I should have said mean squared error. Okay, so rather than sum of squared error, it should be mean squared error. Okay, we're going to do the same thing for model 2, except this time the fit is not fitting a linear model between t and x, but we're fitting a model between t and poly x2. Okay, and so we saw when you do poly x2, you're going to get a matrix where you have one column is x, and the column is basically x squared, but maybe shifted around a little bit so that it's orthogonal and you don't run into problems of collinearity. But basically, this is going to test out a second order polynomial here. And we follow the same process. Once you fit that model, we're going to use it to make predictions. And once we make predictions, we're going to compare our predicted values versus the actual values, square those differences, and divide by n. Okay, and then so this is kind of the code that I'm running, and I've run out of space, but basically I'm doing the exact same thing. I'm just fitting second order, third order, poly 4, poly 5, poly 8, and poly 17. Okay, but basically the same fit, and we're going to basically fit all of these different polynomials for the first validation set. And then once we complete that, then the next iteration of the loop runs, and we're going to have a different validation set. We're going to go through validation set 1, then validation set 2, validation set 3, and validation set 4. And each time we run it, we're going to have a different validation set, and that's also going to change which data points get used in the training set, and obviously the model that ends up getting fit. All right, and so just to kind of show you what is exactly happening when we do our thing, we're just going to take one of the validation sets, and here I just chose validation set C, and you can kind of see how the process works here. Okay, so the black circles are the training data, and then these red dots, these 8 red dots, or 7. Okay, 1, 2, 3, 4, 5, 6, 7 is the validation set. And basically, we remove the red dots, okay, and we fit. So I'm removing the red dots, and we're fitting. First, we fit a linear model to the remaining points. Okay, so I have 21 dots remaining, and I say fit a linear model to these 21 points, and I do that. This is the line that gets fit, and then we say, okay, well, how well does this line that we fit to the training data, the 21 remaining points? That's our training data. How well does it predict the 7 points in our validation set? Okay, so I put those 7 points back, and I say, okay, this is how well it predicted, and we say, oh, you know what? It actually did a pretty good job for 4 of these points, even 5 of these points, and we only had a little bit of error on this point and a little bit of this error on this point, and so the mean squared error for this set of 7 points is 0.0319. Okay. And we would have, something for validation set A, B, and, A, B, C, and D. Okay, so we'd have, different values here. Okay. Again, here is the original data with all 28 points. This is the 7 points in our validation set. I'm going to, again, remove these and now fit a quadratic model. Okay, we fit a quadratic model on the remaining 21 points. And we say, okay, how well does this quadratic model, this blue line, how well does it fit on those 7 points? Okay, and so so we say, well, this is how well it predicted these 7 data points. Okay, and so we get 0.025. Okay, I do this again. This time I'm going to fit a cubic model. So if I remove the 7 red points here and I fit a cubic model, this is the cubic model that gets fit. And we say, okay, well, how well did it predict? How well did it predict the 7 data points? And this is the end resulting fit. Okay, and the mean squared error here is 0.0131. Okay, and again, this is just one validation set, not, and we would have to run this 4 times to do it for all of the validation sets. Okay, I'm just going to keep going. Here it is for the 4th order polynomial, and we say, okay, well, how well did it fit for the 4th order polynomial? So, when you look only at the training data, you go, okay, I guess that did a fairly decent job. Okay. And when you put in the validation set, now we're starting to see a little bit of error here, but it doesn't seem terrible either. Okay. So far fits, one, linear, quadratic, cubic, 4th order, these seem okay. Here is an 8th order polynomial. Even the 8th order polynomial doesn't seem all that bad, okay? But what we'll notice is that, with the 8th order polynomial, okay, it fits this point quite well, right? This is the original thing. But, now we get a little bit of a kind of a tail flip here. And so now we can see, what, we're actually starting to increase the error here, all right? And just for silliness, we're going to also fit a 17th order polynomial, right? And so when you fit a 17th order polynomial on you remove these 7 data points, okay? You remove these 7 data points and you fit this, okay? For the training data, it actually, there's not a ton of error for the data points that are in our training data, right? So if you look at these 3 data points, the line runs exactly through the center of these data points in our training data, okay? And it fits this one quite well. So as far as, how much error is there in the training data, there's very little training error or error on the training data, okay? But when you put in the original validation set, okay, we get this ridiculously huge mean squared error just because when you look at the fitted line here, it does an absolutely terrible job of this, whatever point is here, okay? It seems like it runs, there's a huge value here, okay? And that's just because, with the 17th order, we've overfit the training data, and therefore, it's not going to do a good job generalizing to anything else. And so we get huge amounts of error for the 7 data points that we removed, okay? So, if I just kind of flip through all of these sets, the 7 data points in our validation set remain constant, okay? It's the same set, okay? And we're just, the model that gets fit changes, okay? And so the result is you're gonna get some kind of cross-validation score for each of the validation sets that we have, okay? So when you do a linear fit, if you look at kind of your cross-validation score, you're going to get some number here, some number here, some number here, some number here, and then overall the average, okay? Validation set D is much higher generally than all of the other validation sets, and that's because validation set D happens to contain this one data point, okay, the one that's kind of an outlier, and so you end up getting kind of a lot of error here, right? So you fit each of the 4 validation sets on the different models, right? So you have it for the linear model, the quadratic model, 3rd order, 4th order, 5th order, and 8th order, and you say, okay, how did these things score? And so when you do this, you're going to kind of take the average of these things and you say, okay, what's my cross-validation score? And you have 0.0674, 0.0624, 0.0571, 0.0661, 0.064, 0.0419, and 525 is the average here, okay? So out of these ones, it seems like the 8th order polynomial does best, okay? In terms of the cross-validation score. And the 3rd order polynomial, the cubic one, has the 2nd lowest average, right? And so maybe we would pause and just think about which one would we choose? Would we want to choose the 8th order or the 3rd order polynomial? And if we go strictly off of the cross-validation score, we might be inclined to pick the 8th order polynomial, but it's also reasonable to say, well, you know what, we are subject to randomness, subject to the kind of the random assignment of points that ended up in the validation sets. And so maybe this is not something that holds up in general. And so maybe we could argue to go for the third thing. If you see something that kind of goes against your intuition about stuff, it's worth trying to fit a Kfold cross-validation set, cross-validation thing again, okay? Just because as far as Kfold cross-validation goes, you are subject to error or randomness, and so you can try it again. So if I do run it again, if I just run the exact same code and I change my starting seed to something like starting seed 5, then we see that the 8th order polynomial now has a much higher cross-validation score, okay? Whereas the 3rd order polynomial, its cross-validation score remains kind of lower, consistently lower than the linear and quadratic one, right? So there is Kfold cross-validation is subject to random chance, and so this is something to kind of keep in mind. Here, if I run it again, okay, here, and I have the luxury of running Kfold cross-validation multiple times. You don't always have this luxury, because sometimes you have like a million data points, and it takes hours to just run your cross-validation, and so you might not have the luxury of just running it again with a different starting seed. So here I run it again, and this time the cubic polynomial performs best, and the 8th order polynomial performs better than the 4th or 5th order polynomial, but there's clearly quite a bit of variability here, right? So the 8th order polynomial exhibiting a lot more kind of instability here. And so so our 3rd order polynomial is the best. And so if we just kind of, I've run this 3 times, and it was 2nd best in this run, and it was the best in this run, and the best in this run. So kind of overall, we would probably pick the cubic polynomial in this case, right? And so depending on the starting seed, it's possible to get cross-validation result where maybe a suboptimal model like the 8th order polynomial happens to perform best, right? And so if you are able to run it multiple times, it's not a bad idea, because cross-validation results are subject to randomness, and if you run it multiple times and you're consistently getting the same model performing best across multiple runs, that's a great sign that this is probably the best performing model. If you have the computational power to spare like that, okay? But again, as far as cross-validation goes, this provides no insight as far as like why the cubic polynomial performs best, okay? And what does it mean for there to be a cubic relationship between the year in which the Olympics were held and the winning race time? There's no real insight there. All this is saying is that when you fit the model on some training data and then you use it to make predictions, this one's performing the best, okay? And that seems to be the method of choice for a lot of machine learning models, is we just say, well, I don't really understand what's happening, but can we measure how well it performs on new data? And if it performs well, we say, okay, that's good enough for me, okay? If you want to do this in kind of a more of a production setting, I would recommend against writing your own code like I did like I did here, okay? Although this is, I make you do this for your homework, okay? But in kind of an industry setting, you would just probably use cv.glm, which is a tried and true code, okay? And you would specify k, right? So you would specify k and you said k equal to 4 or something like that. If you don't specify k, then by default, k is going to equal n, and that's going to perform LeaveOneOut cross-validation, okay? And then as far as cv.glm goes, it's going to provide a score, and that's going to be the average squared error. You can provide another function to calculate some other measure of error other than the mean squared error. And so I run this in the following slides, and you'll see there's a little bit of variation because of the random blocks, right? Whereas if you do LeaveOneOut cross-validation, there's going to be no variation because every data point serves as the validation set, and you get the exact same thing. Okay, so here, same kind of idea. We're going to do here. My model is going to be we're going to fit a linear model. So I just do poly year 1, which is a little bit silly. I could just do year. Okay, and we're going to I'm running the cross validation 4 different times. Okay, and so this, we're going to get similar but slightly different results when I do cross validation 4 different times, and that's just because there's variation every time we do k equal to 4. We're getting similar but slightly different results. Okay, here, this is what we get when we run a quadratic model. Okay, so we get something, and again, subject to randomness. Here it is with the cubic model, and you get again a bit of variation from one run to another. Okay. Whereas here, as far as cross-validation goes, I don't specify k equal to 4, and so this is going to run LeaveOneOut cross-validation, and every time you run LeaveOneOut cross-validation, there's no randomness here, and so you're going to get the exact same results when you do LeaveOneOut cross-validation every single time. Okay, so all in all, to just kind of summarize, we can just say cross-validation is a method to see just how a particular model will generalize to new data that hasn't been seen, because it's done by taking your training data, and the training data is not used in the validation set. Okay, and we kind of want to just see, are we running into problems like overfitting? Are we predicting just features of this particular training set that's not going to work out well for new data? Okay, that the same kind of patterns don't work out there. Okay. And so, we run multiple rounds of cross-validation performed using kind of different partitions, different. So if you are able to do it, and the validation results are kind of combined and averaged over the rounds to kind of give just an overall estimate of the model's predictive performance. And it's a useful feature, and I have you run a few exercises in your homework. All right, so we'll end here for today. Last view quiz answer for today is the letter C. C as in cat. C as in cat is the last view quiz answer for today. So you should take that, and we'll see you guys on Wednesday. So have a good evening.